Hey there. I just wanted to work out a couple of more sections here in chapter 17 and get us going on the last couple sections of that chapter. So there's a lot of really cool topics in here, but in the interest of time, I'm going to just focus on two of them. And in this section, we're going to talk about how much real work a battery can do based on, like what are they rated at and what kind of chemistry is happening. So I grabbed a couple of batteries that I got just as a couple of examples. These are some rechargeable batteries that I picked up off of Amazon not too long ago. And so like most AA and AAA batteries, these are rated at typically 1.5 volts. And this would be the cell potential. Probably not a standard state cell potential. So anyway, but the other thing that is rated on these batteries is this number here. It is milliamp hours, mAh. That's what this is. So our AA battery is rated at 2800 milliamp hours, and the AAA battery is 1100 milliamp hours. So let's talk about what that means and think about what it means for what's inside those batteries. So the units that we've used so far have been things like volts and coulombs and amps. And so you can remember that 1 amp is equal to a coulomb per second. So in addition, of course, 1 coulomb times a volt is equal to 1 joule. But joules tend to be really small units, and so we don't tend to use them as often as we do for batteries, talk about things like volts. Okay, so the other thing that I want you to notice is that this amperes is looking at how much how many electrons can you push with this battery in a certain amount of time. And so that's what this is rated at. It says that we can do 2800 milliamp hours. So in other words, we can deliver 2800 milliamps for 1 hour, and that uses up the charge, or some other kind of fraction thereof. So let's take a look at what kind of chemistry is in these batteries and what's happening with them. So if you look at most batteries, it'll say what kind it is. And it's a little hard to see here, but it says nickel metal hydride. I don't think you can see that. It's in tiny, tiny green letters. So let's look at nickel metal hydride and what this is. So nickel metal hydride tends to be abbreviated like that. And of course, we know about nickel. And inside the nickel metal hydride batteries, the nickel is in the form of nickel oxide hydroxide. And the redox reaction that takes place, if we look at the table of reduction potentials, we can find the reduction potential here. So you'll find this equation, and the cell potential is 0.52 volts. Okay, so if you look at this, it's a little hard to tell because nickel is in a compound in both of these. And we have to think about what the oxidation numbers are to figure out actually, like how many electrons are involved in this. So if we do that, we can remember that hydroxide has a -1 ion charge, oxygen has a -2 oxidation number, and that means that this nickel must be +3 to balance that out. And then water, hydrogen is usually +1, oxygen is -2. All right, so we've got hydroxide again, +1, -2, and then over here, this whole hydroxide, +1, -2, only times 2. So this has a -2 total charge here, and that means that this nickel has an oxidation number of +2. So we can see that when we're looking at this half of our redox reaction, there's 1 electron, or 1 mole of electrons, if we are using 1 mole of nickel oxide hydroxide and oxidizing that, or rather the other way around, right? That we're oxidizing the nickel hydroxide into nickel oxide hydroxide. But anyway, there's 1 electron. All right, so that takes care of the nickel part, and then the other part about it is this metal hydride part. So if you remember from when we talked kind of a long time ago about ionic compounds, hydrogen usually forms H+, except when it's in a hydride. And so if it is a hydride, you can notice from the ending "-ide", remember this goes along with anions. Fluoride, chloride, oxide, that means it's an anion. And so in the specific case of this hydride, it is actually an H-. And so that means that this metal, whatever it is, we're just abbreviating with it an M because they didn't specify what kind of a metal it is. This has to have a +1 charge. Okay? So the half reaction involving the hydride is a little bit more complicated to look at and figure out what's going on. So this one is actually written the other way because, oh yeah, I forgot to write it down, but this nickel metal hydride, the nickel part, that is our cathode. So we just went ahead and wrote it in the reduction potential, and that is actually what's happening. Cathodes are reduced. So that means that it is the metal hydride that is the anode. Okay? So we're going to go ahead and write it in the direction of it being oxidized. And if we look at the charge, we can see that this has to be a -1 because this is neutral and this has a -1 charge. This is neutral and this is neutral, and everything else is balanced, so that means we just have 1 electron that's coming out of it, which works out okay here because it's absorbing 1 electron. But there's a little bit more actually going on behind the scenes here. So let's go ahead and look at the rest of these oxidation numbers, because we can see that here we've got a +1 for that metal and a -1 for this hydrogen, and then -2 +1. And then this is metal element, so that actually goes to 0. So at the risk of making this a little too messy, if we go from 0 to, or excuse me, +1 to 0, this also is being reduced, right? So we must have something else that's being oxidized. So if we look over here, we had +1 and -2 for this hydrogen and oxygen, and now both of these hydrogens are +1. And this is a -2. And so this is the change that is taking place. I've got this hydrogen that is a hydride, and it's going to become another H+. So there's actually 2 electrons that are involved in here. But one of the electrons goes and reduces the metal hydride into metal with a 0, and then the other one comes out and is around to go ahead and reduce the nickel in the nickel oxide hydroxide. All right, so I had to work that out because the book sort of goes over it pretty fast. So if you need to slow this down and kind of look back at it and work it out, I always recommend that as a way to see all of how this is going to go. All right, now as you notice, of course, this reaction is just, we're doing some kind of generic M thing right here, right? We don't really know exactly what it is, and so that means we have to just estimate this. But we also can see that these batteries, all of these AA and AAA batteries, are typically rated to be 1.5 volts. So some combination of our anode and our cathode is getting us to something close to 1.5 volts. And if you measure the voltage of a battery, you'll usually find that that's about what it is. So we can just kind of go with that for now. All right. So here's a question. So we've got in these batteries, and one of them is 2800 milliamp hours, and the other one is 1100 milliamp hours, and this one's smaller. Maybe that has some bearing on why it's smaller. Let's figure out how much of the nickel oxide hydroxide, since we actually know its chemical formula, is going to be in these batteries based on this kind of rating. So let's see how the math works. So we're going to start with the AA battery, which is 2800 milliamp hours. Okay, so first thing, we're going to do some unit conversions here. I'm going to turn the milliamps into amps, because that's sort of how things go, right, with my units. And then I notice that an amp here is 1 coulomb per second. So I'm going to go ahead and unit convert that. So I want to get rid of my amp and I want to turn it into coulombs, because that's how we're going to get to electrons. We're going to do that through the Faraday constant. And so 1 coulomb per second, that's handy, except it's sort of messy. So I'm actually going to rewrite this. So notice that anytime you've got a fraction here, that bottom half of the fraction is just going to go down and live with the other bottom half of the fraction here. So let's fix that right now. Okay, so right now our milliamps cancel and our amps cancel, but we've got two different time units. Let's go ahead and cancel those guys out too. So I'm going to convert hours into seconds. So 1 hour is 60 minutes, and then 1 minute is 60 seconds. And if I do the math here, I'm going to get number of coulombs that will be delivered by this battery. All right, so do the math. Pause the video and then come back together, or you can just plow on right ahead and get 1.008 times 10 to the 4th coulombs. They're here. Okay, so remember Faraday's constant is how we go between coulombs and electrons, because it is, 9.65 or 9.648 times 10 to the 4th coulombs in 1 mole of electrons, right? That's where that number came from. So that means I can take this coulombs and actually figure out how many moles of electrons we need to deliver this many coulombs. 9.648 times 10 to the 4 coulombs. So once again, pause the video and go ahead and do this math. You should get 0.1045 moles of electrons needed, or something pretty close to that, right? So now, if we look back at this equation here, we're talking about the nickel oxide hydroxide, because that's the thing we actually can figure out. We can't figure out what the chemical formula of the metal hydride is without knowing what the metal is, and they don't tell us. So we need to know how much nickel oxide hydroxide we have, and we also need to know how many moles of electrons happened in this reaction. So remember, we said that we had 1 electron, just 1, in this reaction that was reducing the nickel 3+ to the nickel 2+. So that's handy. So let's go ahead and set up the math here. 0.1045 moles of electrons, and we have 1 mole of electron coming from 1 mole of nickel oxide hydroxide. And so now we can get the, the moles are the same, right? But we want to know what mass is. So go ahead and take a moment and calculate the molecular weight of nickel oxide hydroxide, and then just go ahead and calculate the grams of nickel oxide hydroxide that should be in this battery. Okay, I get 91.94 grams, and this gives me 9.608 grams of nickel oxide hydroxide, literally, in this battery in order to deliver that 2800 milliamps of charge. Okay. Now, how much of this container, or of this battery, is actually the nickel oxide hydroxide? So I went and weighed this. My AA battery weighs, this specific one, 29.97 grams. So you can see that the nickel oxide hydroxide is about 1/3 of the total mass. And presumably some of the mass is some of the coating and, you know, inside bits that are part of the battery. So that's handy. And hopefully this makes pretty good sense math-wise. And so to test yourself, I would like you to do this calculation again, but for the 1100 milliamp hour AAA battery. So go through this calculation again, just like we did here. Calculate the number of coulombs produced, calculate the number of moles of electrons needed, and then calculate the number of grams of nickel oxide hydroxide. So pause the video and go ahead and do that. And then we'll come back together in just a moment and look at the results. Okay, so I'm not going to write out all the details, but I got 0.04104 moles of electrons and nickel oxide hydroxide. And that turned into 3.774 grams of nickel oxide hydroxide. And my AAA battery, also I weighed it as well. It is 11.64 grams. So this one is also about a third of the total mass. It is the nickel oxide hydroxide. So as you can see, there's probably some limit to how compactly you can put nickel oxide hydroxide in a battery. I didn't see any AA batteries that were rated higher than 2800 when I just looked at Amazon a minute ago, but maybe they will have more compact ways of packing them soon. And so what I hope that you take away from this little short video is that for any battery where you can see what the chemistry is, you can figure out how many moles of electrons you need, and therefore what mass of your chemical components you need in order to make that battery. So I hope you found this interesting, and let me know if you've got any questions.